welcome to track 2. Running untrusted code is code safely is already hard, which we saw in the last talk with Tomislav. But today we're also embedding AI agents into systems that make decisions and execute actions automatically, which introduce an entirely new attack surface. Our next speakers, there were supposed to be 3, then there were 2, and now there's 1. Armned, Robert, and Anit work at the forefront application security and AI red teaming. Between them, they've led thousands of security assessments and even contributed to testing frontier AI systems. Today, they'll show us how a technique called special token injection can hijack AI agents and manipulate their behavior, an attack class that feels eerily similar to the software bugs of the early 2000s, for those of us that are adult enough in the early 2000s. Please welcome Armned.
First of all, thank you, BSides Zagreb, for hosting our talk. And as our host mentioned, there were supposed 3 guys, but it happened to be only me. So we are 3 security consultants, Robert, Anit, and I. We are offensive security researchers that we have conducted some time and effort in AIs and LLMs, where we came up with this new attack that we called it the special token injection. And this talk was previously presented in DEF CON, specifically at the AppSec Village, AI Village, BSides Kraków, and BSides Tirana, and right now in BSides Zagreb. So it feels good to be here. Our experiences include in building AI security practices at Sentry. We also contributed to the OpenAI security research, and we are also part of the Anthropic external AI red team capability, so on and so forth. So without further ado, let's just get to the what you'll walk away with this talk. So the very first thing after this talk, you're gonna have a methodology on how to test AI or LLM deployments in the wild. And this is not a dive deep. This is like more of a broad surface regarding the LLMs, how they work and how to attack them. And we are also going to share some tools that will help you in building some payloads and automating some portions of the test. And after the talk, you'll be able to immediately start breaking and fixing things. So let's get back to a tweet from Andrei Karpathy on August 2024, where he warned us regarding an attack that can affect large language models. Andrei compared this sort of technique to the classic SQL injection that affects web applications or any application that has a database integrated. And similarly, special token injection is an attack that affects large language models by parsing some sort of weird tokens, like this one over here, the end of text, where the proof of concept that Andrei showed us was upon pasting that part of token in a chatbot, it forced the LLM to generate the text, which was a very weird use case. But before we actually see how to conduct the special token injection, let's just first take a look on how modern LLM works. And also, I would highly appreciate if anyone has any questions throughout the conversation, feel free to interrupt me, raise your hand, and we can proceed with the questions. So modern LLMs support like a role hierarchy for the chatbot. Like we have the system message where it can be anything like you are a customer support agent, so on and so forth. And then the agent or the LLM can respond with, how can I help you? And then the user request can be something similar like, can you get me a ticket to Las Vegas? And then the LLM does some reasoning or some thinking, they do some tool calling, and then finally they generate the message on guiding us how to get a ticket to Las Vegas. And what happens if in this part of the user message that is supposed to be controlled by the user, what happens if we parse some sort of special tokens that are used to force or to cut short the message of the user, which is the IM end, we stand for the start message or end message over here. which closes the part of the message that belongs to the user role. And right after that, we are parsing another special token, which is the mstart, followed by a system label, which forces the LLM to think by spoofing a new system message throughout the user role prompt. And in order to conduct this attack, what we also did was we also placed another MN token, another sort, and then we forced some thinking for the model. And what this caused the model to behave, instead of the model to fulfill our needs on behaving like a chat support agent, now the agent is the Hexor agent and is up and ready to write some shellcode from us. I know this may sound a bit overwhelming at the first sight, but to fully understand it, let's just come up with a sort of definition on what special token injection is. And special token injection is not a prompt injection vulnerability, just so that we are clear. Special token injection is a vulnerability that attacks the tokenizer of the LLM. And the tokenizer is the technology in LLMs that is used to convert the natural language of the user to some sort of token IDs that the model can interpret and the model can understand. And the next step that what happens is the model generates a few tokens more that are once again parsed to the tokenizer, and then the tokenizer decodes all of these tokens, and then we can see the text. So what happens if we are able to inject some sort of tokens that have some higher entropy or that are higher privileged in the sense of the tokenizer? That's when we talk about special token injection, where we attack the tokenizer and the structured prompting protocols like ChatML. Now, let's just first try to understand two differences between modern LLMs. We have the base models, and then we have the struct models. Base models are the one models that are very good at completing a text. And they are the pre-trained models that cannot engage in user messages, or they cannot engage in like very long chatting schemas. They do not have the capability for function calls, so on and so forth. And in addition to the base model, we have the struct or the instruct models. These models are the fine-tuned version of a base model. And these models are fine-tuned to be able to be used by humans, communicate in a very long chat, use function calling, do thinking, so on and so forth. In this area over here, we have highlighted these two tokens that are the special tokens for a particular instruct model that instruct the agent that this is the start of the message and this is the end of the message. The reason why struct models use this sort of special tokens is to know when a message is starting and when to cut short a message, or when is that message going to end. Like for instance, this part of the tokenizer, or the message that we are sending to the LLM, the message that we sent was, can you get me a ticket to Las Vegas? But how this message is going to be parsed to the model is by having this special token over here, the role label that we are the user in this case, and then the end to tell the LLM that this is the message. This is where the message is starting, and this is where the message is ending. One thing that is very important throughout our research, we didn't really know where to find the special tokens, and we didn't really know that different models support different sort of special tokens. The reason is because different models use different vocabularies, and with different vocabularies, we have once again different special tokens. So this is another example on how the messaging structure looks like from an attacker's perspective, and the key areas where we highlighted on the specific payload that we used to perform special token injection. This particular example in this case is to enhance the jailbreaking capabilities, but special token injection is an attack vector that can go way beyond jailbreakings. In order to understand special token injection, we have categorized it under three main categories: the raw user input, the one with the special tokens through the comparison tags, and the other one is, we call it the chat completion schema. We are going to talk about it shortly, and then the chat template, which in most of the cases is a Jinja 2 template. And then upon having from all of these sources the user input, the Jinja template will produce the output, which in most of the cases is ChatML, and then we have the tokenizer that generates token IDs, and then we have the sink where in this case is the model. So let's just see how can we create some payloads in order to achieve special token injection. In this area of the presentation, highlighted in green, we have a very short list of some of the most common special tokens we have seen in the wild, like the mstart to specify where a message is starting, the mend to specify where the message is ending, so on and so forth. All of these tokens, all of these special tokens have weird functionality on their own. Like for instance, we may see a function call that is tools to start a tool call, and then the tool call to close the section over here, and then we have the tool response, and all of these tokens in the first site do not really make sense. And what we did throughout our research, we came up with this application or a tool which we call it the Token Buster. Token Buster helps you to create special token injection payloads on demand. It supports more than 1,000 models, and in this section over here, you can select the model, and you can see in real time the user input, how it is going to be sent from the user's perspective. And then we have the chat template this particular model uses to generate the output, which in most of the cases is ChatML, like the one over here. And then finally, we have the token IDs for every part of the message that is going to be sent for the model. And in addition to that, we are also giving you another tool, which is called CRI Inject, which is a tool to attack chat completion insecure LLM API configurations, where in the JSON payload, a user can swap the role from user to system or assistant, so on and so forth. This is just a screenshot from the CRI Inject tool. And now let's get back to creating custom special token injection payloads for models. Assume that this is the message that we are sending to the model. Once again, we injected the mstart, followed by a role label system, but keep in mind that this particular message is being sent under the user role. And once we send this message to the LLM, it must firstly undergo the chat template conversion in order to convert it to the ChatML schema, which is the structured prompting template that all of the LLMs use. And after this particular message is generated, then we are going to have a set of token IDs that the model can understand, and we can note some tokens that have, in our case, a higher value, like 100 to 64, 100 to 64 over here to 65, so on and so forth. The reason why we highlighted these specific tokens is that the values of these tokens are the mstart and the mend. But what is the worst case scenario? What is the worst case scenario that could happen in the wild through special token injection? This is a screenshot from a pentest that we had at Sentry, and what we did in this case is we literally used that same payload, and the AI assistant that was supposed to not engage in illegal or illicit activities now is up and ready to write C# shellcode loaders for us. where the agent, instead of following this particular system message, now the agent is Hexor. Now that we saw a very brief or a high-level explanation of special token injection, the biggest impact and my most favorite impact of special token injection is the capability to hijack the model's function calls. With function calls, we mean if the model can read a file, if the model can execute code, or if the model can browse, so on and so forth. All of these function calls can be hijacked through STI. But before we go to the actual exploitation of function callings through special tokens, one thing that is very important to understand is the way how function callings work in LLMs. So assume that we have an LLM that has the capability to execute code. So we prompt the model to read a particular file, and then the model must firstly suggest the tool call to itself. Only then the model can execute it. And if that particular tool call is suggested by the user, the model will never execute the tool call, strictly because LLMs are built to trust their own input. So a tool call is firstly suggested by the model, it is then executed, summarized, and then the final output is parsed to the end user. So in this case, what we did, we forced the model to repeat a string. And the reason why we forced the model to repeat a string is that throughout this exploitation technique, we force the model to auto-suggest a tool function to itself. And upon providing this particular tool call, where we parse and execute SQL query, which was a legitimate function call to the LLM, now the query that we have pasted to the model is to select all employees, do this and that. And in addition to that, we also added this query over here to insert a new employee into the database. And once we sent this message to the LLM, these special tokens were automatically triggered by the LLM. So we forced the LLM to suggest a tool call to itself. The model did that, and then finally, the LLM summarized its result and told us that Hexor was successfully added in the database. Initially, we thought that this was some sort of hallucination of the LLM, and what we did, we navigated to the database because it was a lab that we have developed in our own. And once we navigated to the database, now we can see that the model has successfully added a new entry in the database. Now, in addition to the raw special token injections, special token injections are most commonly identified in open source models. And special token injection equivalency in frontier models like the ones in OpenAI, Gemini, so on and so forth, they have something in common, which is their API or their messaging structure. They all use the same messaging format. Like it's a JSON array that has a messages, and messages is another array that contains all of the messages for a single interaction with the LLM. And what we did in our case to showcase how special token injection can work in API, we created a multi-agent system where the first agent was the biochecker agent. The goal for this agent was to check if the user input was related to biology. And the only output that the LLM we wanted that to generate was bio-OK true or false. The next agent that we had was the triage agent. The triage agent had a task to hand off the query of the user once the biochecker agent has returned true and the execution flow reaches the triage agent. This agent can pass the input to the next agent, which can be the French agent, Spanish agent, or the English agent. The task that we wanted this particular agent to do was to translate the answer for a particular question. The intended workflow for this specific use case was in cases that the user query is not related to biology, and the query is something like, what is JavaScript? Then the biochecker agent would respond with false, and then the execution flow would immediately stop. However, however, if the message sent by the user is to explain DNA in French, then the triage agent would detect that the query is biology related, and because the user requested an explanation of DNA in French, it automatically hand off the query to the French agent, and then the French agent spoke French to us, which is something that I don't really understand, but it's okay. Now, the messaging structure that we have developed to communicate with these agents had this format. The messages, this is the default format that every LLM in the wild supports. So every LLM supports the role over here and the content that we are sending to the agent. And what would happen if we swap the role from user to system? Does it mean that we are injecting a new system prompt? Does the system prompt override the previous system prompt? Or will it append a new entry into the conversation flow in order to attempt and poison a new system message for the whole workflow of this multi-agent system? So in order to come up with an exploitation, what we did in our case, we injected a new system message. And the system message that we injected in this particular case is to force the biochecker agent to always respond with true. Because the user input must firstly go to the content filter agent, and only then the content will be passed to the next agent, where in this case was the English agent. And in addition to forcing the biochecking agent to always respond with true, what we did, we added another instruction to the LLM to pass the handoff to the English agent always, and to induce it to write some shell code for us. And then the whole schema of the messages would go from the attacker to swap in the role from user to system to inject a new system prompt, and then from that perspective, the attacker could easily hijack the functionality of the LLM. One of the things that we have discovered in the wild, we discovered a browsing agent that utilized this messaging format where we could force a new system message for that particular browsing agent. And what we did to showcase the exploitation, we added a new system message to this particular agent, and then we did some vibe hacking, and we navigated to the labs of Portswigger, and we forced the agent to complete the labs for us. So this is just an example on how one agent can be hijacked to perform unintended and potentially dangerous actions in the wild. The next one, the next source to attempt identifying special token injections is through the Jinja templates, or specifically this attack. What if in the Jinja template that every model uses, what if we can tamper with that? Or what if the model fetches an untrusted Jinja 2 template, and that particular template contains a custom role? And what would happen in that case is that we are injecting a custom role, like in this case we have the Zentry role, that is equivalent to the role of a system message. And just because in our instruction over here we said that if the message role is Sentry, basically to set the system prompt message content under this particular role. This sort of attack where we need to hijack the Jinja 2 template is probably the hardest one to carry out, because you need to firstly compromise the host where the LLM lives, and where the LLM lives, the Jinja2 template lives there as well. So you might need to firstly compromise the host, and then from the perspective of the host, you might want to come up with this attack. But if you compromise the host, then probably you could do some more nasty stuff rather than modifying the Jinja2 template. All right, so one thing that we did in our research, we had all of these hypotheses on what we can, but what we could actually do with all of these items. What we did, we created a multi-agent LLM jacking through the means of STI. So we identified like lots of agents in the wild that are vulnerable to this attack. We repurposed every piece of agent to conduct a small piece of work under our own desires. And our own desire in this case was to write a shell coding loader agent. So basically combine lots of agents from the wild, reconstruct them to achieve our goal. And the best part of it is that we spent literally $0 to achieve our goal. Now we have a video which is supposed to play, but I think because I'm on PDF, it won't play. But I'm going to walk you through on what this video is supposed to do. And in case anyone wants to take a look at the video, please reach out to me after the talk. I'll be more than happy to share it with you. In this video, we have a Python code where we can see in action all of these agents. Some of these agents were the healthcare agents, or customer support agents, browsing agents, so on and so forth. And through the means of STI, we have reconstructed every piece of this agent to make them write some shellcode loading for us. Now that we know how to attack through the means of special token injection, let me categorize on how hard is it to validate and to remediate these findings. The raw user input through the raw special token injection is probably the easiest one to exploit, but the hardest to validate. In cases where you don't have local access to the LLM, from a black box perspective, validating that the exploitation worked at least last year was harder just because models were weaker and had lots of hallucinations that could make you think that a particular payload worked, but maybe the payload did not work. This is an issue from Hugging Face, where through the means of applied chat template and the split special tokens, they claim that this vulnerability is fixed. However, marking this particular argument, split special tokens, as true to basically prevent users from injecting special tokens in user input, there can be side effects, as the Hugging Face team have mentioned. And the reason why there could be side effects is because the model would then never know where or when to close a message, when to invoke the tool calls, and it would be impossible for the LLM to be helpful to its human. The next category, which was through the chat completions API, this is by far the easiest one to exploit and the easiest one to validate. And in addition to validating, it's also the easiest one to fix, because this functionality, this part of exploitation works through the API. What the developers need to do is prevent end users from manipulating with all of these role parameters through the means of user input, because the user input must always be marked under the user role, and in addition to the user role, that part of the prompt must only be a string, not be an array, so on and so forth. I can also share a blog post that we have wrote specifically to tackle this this issue. And the last one is the hardest one to exploit, but it's the easiest to validate, just because we need to firstly compromise the host, modify the Jinja template, and then we can validate the special token injection. Now let's talk about the blast radius. Throughout our research, we have identified like lots of vulnerable agents in the wild. And through the means of special token injection, we have validated that 1 in 3 agents are vulnerable to special token injection. One thing that we had like open questions, our research was mainly conducted in Llama CPP and the Transformers library. We had lots of open questions like which else providers, in addition to Llama CPP and Transformers, which of any other providers do not split the special tokens? And how many of these providers are vulnerable to special token injection? We kind of have that answer right now, and most of the providers that allow you to deploy models locally, they are all vulnerable to special token injection. And one other question that we have is, can thinking or reasoning models use STI on themselves to break alignment? And we have also listed a few resources. And after the talk, anybody who wants to catch up, talk more about special token injection, please feel free to reach out and have some talks.
Thank you, Armned. Any questions?
So when you self-host open source models and use open source inference engines, I guess you have control of what the content and the look of the chat template will be. So I was wondering, like, if there's a way to harden that template or use some techniques to prevent this, or is the mitigation done at some different levels of the model?
Do you mean the Jinja template?
The chat template.
Yeah. So if the template lives in the host and end users, like the one users that communicate with the LLM through the means of an API or whatever, if the user does not have access locally to the chat template, they cannot modify the Jinja 2 template. But there are plenty of Jinja templates in the wild where if you add like a system role, the previous system role that was set by the developer, it will be overwritten. So now, depending on the model, it depends also what kind of template the model uses. Different models use different templates. So my suggestion would be to take a deep look at the template that is being used and use Token Buster, which is our tool over here. You can host the Token Buster locally as well, by the way. Just let me reach this. So what you can do in this case, you can select the model that you are using, which will automatically populate the template that is being used by your model, and you can see in real time how the conversation flow works from the user's perspective up to the generation of the content from the model. And there are some cases like in when a user swaps their role from user to system, this previous system message will be overwritten automatically. And it all depends on the way that the Jinja 2 template is configured. But for the attacker, in order to manipulate the template, they must compromise the host firstly.
Yeah, or I mean, it could be like misconfigured if you change the content of it. But I guess I can validate it with this, so that will be really useful. Thank you.
Anyone else? Yeah. Till I reach him. So do you have any advice for developers who are writing these agents that they can do to avoid such injections?
Yes, for raw special token injections, the user input. Now developers must firstly know what model are they using, and depending on the model, they have to check the tokenizer files locally, where all of the special tokens are in a JSON file, and map all of these special tokens that can be used by the model and create a custom logic through the API, so that if the user input contains these special tokens, to basically automatically remove them from the from the user input. That's for the raw special token injection attack. For the API, users must never be able to send an HTTP request that has the body data very similar to this. Because what an attacker can do, they can literally add like tons of messages in a single HTTP request, which will result in higher token consumption. Or what an attacker can also do is basically create like a spoofed messaging schema, and depending on the implementation, the impact differs as well. So in cases that that particular model has tool callings through the means of this HTTP request, tool callings can be hijacked, or the model can be jailbroken, so on and so forth.
Hello. Is there any way to access the Jinja template, not to modify, just to access it without compromising the actual machine?
So the question was, is there a way to access the Jinja 2 template and modify it on the run?
No. Without modifying, is there any way to view it?
To view it, yes.
Yeah.
Yes, if you are using local LLMs, yes. Every local LLM has the Jinja 2 template embedded somewhere in the files. Once again, if you use Token Buster, you select the model of your desire, the chat template will automatically be populated depending on the model.
No, my question was actually from an attacker's perspective. So if I want to see what the Jinja 2 template looks like on an LLM that I'm trying to compromise, am I able to pull it out or download it or grab it so I can see the template as it is?
It depends. It depends. It depends on the deployment. If somehow, some way, the developer makes the template publicly accessible, then the answer is yes. Under default settings, then the answer is no. However, if the attacker knows what model is being used, then they can know what the Jinja 2 template looks like, unless the Jinja 2 template has been modified by the developer. So it all depends.
Just give me a second. I'll be right there. So it's 2026, and we're dealing with input validation all over again. I'm happy that that we've reached this far in technology.
Is there a way to enumerate which model is being used?
I mean, there are plenty of papers in the wild that argue that you can fingerprint the model, but I didn't validate it. I mean, I've had cases where I asked Claude 4 point something, and it told me that I am DeepSeek, and vice versa. I asked DeepSeek on which model is this, and it told me that, hey, I am Claude. So
Thanks. Thanks.
nice. Any other questions? If not, feel free to catch up after the talk. I would love to talk about it.
Thank you, Armned. Before you leave, public service announcement. On the ground floor, there's a CTF house if you want to participate, if you want to have fun.